Hello, good morning, everyone. I'm really very happy to be with you today. I thought to record this session to be with you, and it's gonna be the final revision before our next midterm. I've already recorded a long revision through the last sessions, two sessions actually. I dedicated the first one to review most of the course notes and the propositions, which is really very important going through each part of the part that we covered together. Then in the previous lecture, we already dedicated enough time to go through the uh, uh, one of the previous midterms in details to see how the 10 questions of the midterm are formed and the idea and the theoretical background that's required in order to go through each question of these questions. Today, I will finish up with the last year midterm for this set of revisions. Hopefully, it's going to be enough. It's not just only how to go through the questions, it's how to think and to choose which part are you going to go through it. Of course, the nature of the exam is not easy. It needs someone who really did a good job in studying, reviewing most of his course materials, and familiar with the activities and frequencies. And that's what we did. And this is what I have tried to explain to you from the beginning of our course, maybe from the first lecture for this year and the previous year. I started to insist on this tip. Just walk through it, don't give up, and step by step, you will gain the enough momentum for you just to make a perfection in thinking and making decision in exams like this. Okay, I don't want to waste your time, so I will start with the following questions, inshallah. Let's see the first question, and was almost around this time or period of the year. It was on the 30th of October in last year. That was the first exam in our midterms. Of course, you know that the first midterm is going to be a 40% and the second will be 60%. And the sum of them, if you got greater than or equal to 9.5, so you will pass this course. The first question is asking you to indicate which statements are true. As I told you, in most of the questions, this is going to be the head of the questions. State or find or define which statement of the following statements are correct. And he started this question by asking you if A was a square matrix and it is a Hermitian. Oh, stop. So I will have to review in my mind what's a Hermitian matrices. Once more, if A is a Hermitian and invertible matrix, then for any alpha, for any number belongs to R, the matrix which is alpha times A, which is a Hermitian, plus A minus 1 is also Hermitian matrix. So actually, this question targets the definition of the Hermitian matrices. It's really very simple. Let me just get my laser pointer and we will be together. Okay, so the first is to state what's the Hermitian matrix. Hermitian matrix is a very unique matrix which contains two specific operations. Number one, it's the conjugate and the transpose of this matrix is going to be exactly the same of the original matrix. The conjugate and the transposition of a matrix, it is what's called an A star of this matrix. يبقى for Hermitian matrices, the main issue is if you got the star matrix, which is simply getting the conjugate and the transpose of this matrix, it will equal to the main matrix. So it's the conjugation and the transposition equal to the original matrix. Of course, there is a skew Hermitian matrices. What's the skew Hermitian matrices? A minus A star will equal to negative of A. So you should review this part. Okay, remark for this one. So multiplication for Hermitian matrix by a constant, it will be reserve the process of this property, and also will not affect the nature of the matrix. It will remain Hermitian. So the multiplication will keep your matrix to be Hermitian, and also the A minus 1 is gonna keep it. So this is correct answer. But first of all, let's do it once more. A is an n by n Hermitian and invertible matrix. Then if we multiply the matrix A and add it on A minus 1, the result will also be Hermitian matrix. It makes sense. For question number B, for any matrix A belongs to the set of n by n matrices, and for any alpha belongs to R, the matrix alpha A minus A transpose is skew symmetric. Any symmetric means skew symmetric. For this question in specific, we don't, he put the alpha to manipulate you. Because if you multiply a constant value in a symmetric matrix, it will stay symmetric. If you multiply a constant number in a skew symmetric matrix, it will stay as a skew symmetric matrix. For you to remember, if I added a matrix plus its transpose, I will have a symmetric matrix. If I got the subtraction of A minus AT, it's going to be a skew symmetric matrix. So once you have a skew symmetric matrix, you multiply it by alpha or beta or whatever, the result will stay the same as skew symmetric matrix. And this condition or this one is okay. So it is a correct answer. So if choose the E, choose the E. I'm reading very carefully. Any matrix transposition subtracted from itself is a skew symmetric and it's not going to be affected by the constant number. Now, he giving you a matrix which is 4 by 4, as you can see, with the last row equal to zeros, and he is asking you, is this matrix is in reduced row echelon form? So the appearance, first of all, it's a 1, 2, 3, 4, and 5. I'm sorry, it's a 3 rows and 5 columns. So I'm expecting for a reduced echelon form that it's not gonna reach an identity matrix because it will lose some of its pivots. So if you look closely to this matrix, you will find that the second row does not exist, but the rules of the reduced echelon forms already exist. The zeros on the left, then you will have a pivot, which is 1. Go to the second of the zeros on the left, and for the first or for the above row, the first non-zero also positive 1, and for the last row it is all zeros, so it is correct. It is in reduced echelon form. As I told you, just check the pivots of each row, and we'll find that it is reduced echelon form. He asks you again for number D. There exist AB matrices with a square matrices such that A is invertible and B is not invertible, but AB is invertible. It may happen. So it is not necessarily true. So not necessarily true, which means maybe it is you will have this situation, but I can't consider it as a general case. Any zero matrix is symmetric and is in reduced echelon form. Let's discuss this assumption. Partially true. Any null matrix is symmetric and in reduced echelon form. Only it is a square null matrix. Because he told you any zero matrix. So you are exposed to cases where you will have matrices with a null, but 3 by 2 or 2 by 3 or 5 by 4. So it's not a square matrix. So for this statement to be true, Okay, just don't answer from the gate. Just think thoroughly and try to choose your alternatives very well. Yep, any zero matrix is symmetric, that's okay, and is in reduced echelon form, that's also okay, but under one condition, it is a square matrix. So as you can see, even for the right stuff or the wrong stuff, you will have to read it carefully. Some of the statements will be obvious for you. Others, you will have half of the statement is correct and the other half is not correct, or it can't be generalized. So you should keep this in mind in all questions. This is for question number one. Let's go for question number two. From the look of this question, even before we go through it, he is asking you, since you have an augmented matrix, now I've studied my lessons very good, and I know by the look what he's going to ask me because I'm familiar with the nature of these questions. So now he will target the part of the classification of a solution of a system of equations. It must be like this. So let's read it. He is giving you for each alpha belongs to real numbers and for beta belongs to R, consider the system of linear equations over R. This is a system of linear equations over R. Whose augmented matrix is given its front of you? So first thing to do in this question, try to reach first as possible, or first as you can try to reach an echelon form. So just give it a look. It will enhance your choices in unbelievable way. Then test the choices one by one. So if I give a good look for this matrix, I will discover that the first row contains 1, -1, and 0 and 2, blah, blah, blah. But the second row for the first column is correct in the echelon form. But for the third row, I will need to do just a small adjustment and it is accessible. If I added the first row directly on the third row, I think the situation will be a lot better because you will generate two zeros in here. B minus 2 will stand alone, and the T minus 2 will erase each other, and that's gonna be P. So you will get benefit from this. And also, if I multiply the second row by negative sign and add it on the first row, it's really very simple to reach the echelon form. I want you once more to remember that the classification of a system of equations, we have inconsistent system. The rank of the smaller matrix doesn't equal to the rank of the augmented matrix. The system will be consistent once they both share the same rank. If these share the same rank and they equal to the number of variables, it's called a determinant consistent system. If they equal to each other but less than the number of variables, then you will have indeterminate consistent system, and the degrees of freedom equal the difference between the number of variables and the degree of freedom that you have. So now let's put it on echelon form. As I told you, I will add the first row to the third one. And I will multiply the second row by negative alpha and add it on the last row. And that's the shape that I have. Look to the coefficient matrix, which its last column is 2, 1, 0, and alpha. And this is the result. Okay, he is telling you under these conditions, state which statements are true. This is gonna enhance your life a lot. The question number A, if alpha doesn't equal to 0. If alpha doesn't equal to 0, means the last row will be non-null. It's not going to be a 0 row because this value doesn't equal to 0 and that value doesn't equal to 0. And also for beta doesn't equal to 2. And for this guy, he will never equal to 0, which means the last row exists, the last row exists, the row above the last row is also exists, and those two rows, they have numbers. So he is asking you, then the system is a consistent system with unique solution. He's asking you about this, and of course, yes, because the rank of the augmented matrix will be 4, exactly like the coefficient matrix. So both of them are equal to each other. If I want to test the second statement, he's giving you alphas equal to 0. So the last row is eliminated. The beta is equal to 3. It doesn't equal to 2. So this guy or this pivot exists and this value exists, which means you will have a rank of 3 and I can continue. He's asking you, then the system is consistent? Yes. And underdetermined? Yes, of course, because you will have 3 equations or 3 rows, but in 4 unknowns. With a degree of indeterminacy of 1, yes, it makes sense. You will lose just only 1 row. So the rank is 3. So the degrees of freedom is 4 variable minus 3, 4 variables minus 3 rows, which is going to be 1. The solution set, okay, simply after you put alpha is equal to 0 and the beta is equal to 3, just try to isolate A, B, and C, and you will get the values as you saw. We did that previously, so I don't have to do it with you step by step. If B is equal to 2, let's test this one. Then for any value of alpha, the system is consistent. Let's try this one. If I put beta equal to -2 on this guy, so for the smaller matrix, which is the coefficient matrix, you will have 0, 0, 0, and 0, which is the rank will miss one of the rows. While the other matrix or the bigger matrix, beta doesn't equal to any value, so or it will be any value. So for this system, it's gonna be inconsistent system. يبقى 4 betas equal to 2. This row will force the rank of the coefficient matrix to be less than the rank of the augmented matrix by 1, and so it's an inconsistent system, and it is the correct answer. If alpha is equal to 0, it means I lost the last row. The beta doesn't equal to 2, so the second row remains. Then the system is consistent under determined with a degree of indeterminacy of 2. This is not correct. We already approved number B that it is with a degree of freedom of 1. If alpha is equal to 1 and the beta is equal to 3, then the system will have definitely a unique solution, but once you try to solve it, you will have a solution different than this result. So you will have to solve it, continue on a reduced echelon form, and you will have your solution and compare the results. One of the repeated remarks on those exams is that you may have exactly the same set but missing a sign but replacing the values. So you should be aware about your steps and the possibility of this to happen. If I go to question number 3, this is one of the standard questions in this part of the exams, and usually test your knowledge about the elementary matrices and the elementary row operations. It needs a focus, and this part is really very important. I've explained it for you more than once, so please go through it step by step. He's telling you, let A belongs to the set of 3 by 3 matrices, and B an arbitrary matrix, and consider B is obtained from A by performing the following row of transformations. The first step, guys, is to try to write this group or bunch of steps into elementary matrices. The first elementary matrix will change row number 1 instead of row number 2. The second elementary matrix that you will need is to multiply the third row, in 5. And the third operation is adding to the third row a multiple of 4 from the first row. So, which can be easily written like this. This is A. The first operation will be switching rows R1 and R2. The second equation will be multiplying R3 by 5. The third equation adding to R3 multiple of 4 of the first row. those exactly the order of the operations that you will apply in A. So that's the first one to be applied in A. That's the second one to be applied on both of them. That's the third one will be applied on the whole set. And that's going to be the result, which is B. Okay, very good. Let's go through the questions. He is asking you once more, under these conditions, indicate which statements are true. If A is I3 لو ال A كانت I3 يعني ال E matrix is the unit matrix. Then B is invertible. Then B it's gonna be invertible. And the B minus 1 will equal to all of these guys. I will do this step by step. I will start with replacing A by the unit matrix. Then I will try to get the inverse of both sides. This is B minus 1. And to get the inverse of these 3 multiplied in each other elementary matrices. Of course, getting the inversion will reorder this operation. So I will have ER1 and R2 starting from the far left, and the ER3 for R1, it will go instead of the first step. And each one of them will be reversed. So which means R1 and R2 will go in the first position from the left side, and the inverse is still the same. For the matrix in the middle, I will reverse this operation, multiplying the third row by 5. I will multiply the third row by 1 over 5. And for the other operation, I will replace it also, but instead of adding a multiple of 4, I will add a multiple of negative 4. This is exactly how it should be look like this B minus 1, which means that B minus 1 will equal to R1 minus R2. I thought it's better to write it to you. Of course, it's not going to make a difference, but I wanted to write it to you in order to be able to compare it easily. So R1, R2 switching. This is R1 and the R2. Yes, they are already switched. Multiplying R3 by 1 over 5, which is, yes, it's correct. Adding to R3 multiple of negative 4 from the first row, yes, also already exists, which means the first one is correct. Now, the rank of matrix A is equal to the rank of matrix B. Now, this is one of the advantages of the equivalence of the row operations, that the rank, okay, through the main row operations is gonna be exactly the same. Yes, it's correct. As we are doing only row operations, so it will keep the rank. Okay, for number C, it holds that if you reverse the operations, so I will move from B into A. I will move from B into A, replacing the equation or inversing the equation. Okay, so move from B into A, I will move, okay, from B into A2, which means I will reverse this operation, which is gonna be L3 minus 4 L1. Then I will reverse this operation, which is gonna be 1 over 5. And then I will replace this equation, replacing the root. So I will start first by writing B and A. The B matrix, the first operation will be multiplying the first row negative 4 and add it on the third row, as you can see. The second operation on both of them, I will multiply by 1 over 5, okay, in order to go to matrix A. And the last operation from this row, I will do the reverse order between R1 and R2. If you look closely to these 3 operations, you will find the order is destroyed. This is supposed to be B. So the first operation is R3 plus 4 of R1, not 1 over 4, plus it's destroyed. So this is the correct answer, and I'm not going to choose that guy. Here he told you if A is an I, لو ال A دي هي اليونت matrix, ال A is the I matrix, then B transpose gonna be those guys. And here he is testing your understanding about the transposition of a certain matrix. From the beginning, I have A, this relation, which I have B I matrix, which is times the 3 row operations that exist, all the elementary matrices, that exist in your eye, in front of you. I would start with them. Then I will start writing the transposition. The transposition with the elementary matrices, sometimes it make a difference in the matrix, and sometimes it will keep it this way. Yani, for example, for the first matrix, if you remark, I'm replacing the first row with the second row. If you try to make a transpose, it will stay the same. The matrix will be exactly the same. So, but for this guy, if you try to also for the second matrix, if you try to make a transposition, it will be the same. For the last one, if you try to make a transposition, it means you will replace the rows through the transposition. So I would write, of course, I would write the R1, R2 with the order, but with remarking that when you do transposition in multiplication, the order will change exactly like the inversion. So actually, for the steps that exist in here, this is the steps of B explained by the three elementary matrices. I will replace the order and then I will look through the meaning of the transposition. So replacing will bring R1 and R2 at the beginning. 5 R3 will remain the same, but this guy will change. This guy is going to be R1 plus 4 of R3. That's R1 plus 4 of R3, and that's what exists. So it's a correct answer. And that's a very good question. For the last one, which is number E, he is asking you if you have this row operation on A, are you going to reach for B? So all I have to do is just to review those guys and indicate them with those ones, and the order is not correct, so it's not going to be correct. As you can see, the question is very delicate, just containing the process or stressing on the process of how to multiply, how to do the inversion elementary matrices. Even he went a further mile to the transposition and the relation between the transposition of matrices, which is usually confusion, or contain a lot of confusion with plenty of students. It's solved in front of you. Please do resolve it again. Okay. For this question, which is question number 4, this is a direct question, and I told you about this plenty of times that in most of the exams, usually you will have a direct question, just only one of them. He's asking you to find the inverse of this matrix, which is really very simple. We can do it either using Gauss elimination or to use it through the cofactor method and getting the algebraic complements and so on. So that's a very direct question. Please try to go through it carefully. And mainly for those questions, I would, as I told you previously, and as I've advised you, please have enough sleep for your mind to work perfectly. So question number 4 is very, very simple. Going to question number 5. He is asking you to indicate which statements are true and giving you A, which is a matrix n by n, satisfy the equation a squared minus a plus 2n, then A is invertible. Of course, if you look and read, you will stay a little bit. Let's do it once more. A is an n by n matrix. Satisfy the equation, which is a squared minus a plus 2i is equal to 0. Once this matrix is satisfying this equation, for sure A is invertible. Why for sure A is invertible? Because simply you are getting A times A, which is related to the matrix A, minus A, which is related to matrix A, but you are adding on In, and In, it's a matrix square with the same rank, so it will keep the rank, it will ensure that those ranks are exactly the same like the In, so it is reversible. So makes sense, it's correct, as it has an addition to the identity matrix. It had the same ranks as indicated, so it is invertible. It's a very nice question. So this is correct. Okay. Test number B. Test number B, he is giving you, and that's by the idea. This question, it's really very close to another question that we already solved previously in last year exam, or in the exam that we already solved together previously. So all I have to do is to start from this guy and try to reach that one. It's an application on your experience in multiplying from the left or from the right for a certain matrix. So I would start with the given, which is b minus 1 cxa equal to d. Okay, I need to isolate the x matrix, which is really very simple. All I have to do is to multiply the matrix from both sides in B. So it's gonna be times B minus 1 and the B times D, that's the first step. And I will multiply from the right A minus 1, both D and A. So now I have B by B times B minus 1, CXA times B minus 1, and on the last side, it's exactly the same. If you remark, I've multiplied B from the left and the A minus 1 from the right. Let's look to the left side. B and B minus 1 will be eliminated. It will be I. A minus 1 will eat each other. You will have the identity matrix, which means I have just only CK. And now I have B, D, A minus 1. I need to get rid of C. So I would multiply from the left in C minus 1. C minus 1, it will appear in here, but will make C minus 1 and C disappear. So that's the final result. Look at this guy and look to the result that he's asking you about. C minus 1 really exists. Okay. Oh, but by the idea, I can't replace the order. So it has to be the same order. He gave you the same symbols, but he just slightly it changed the spaces between their order, which is not acceptable in matrices, as you know, because multiplication matrices is not commutative. So this guy is not a correct answer. Point number C. System AX equal to B, where A belongs to the set of n by n matrices, and it has a rank n in consistent system, والرانك بتاعها بيساوي m. يبقى تاني once more, system AX is equal to B, where A belongs to the matrices m by n. So remark that the number of rows is equal to m and has a rank n. Is a consistent system? Of course, this is correct because it makes sense at the coefficient matrix and is apart from the augmented matrix, and both of them will keep the n, so it's a consistent system of equation. Number D, for any matrices, AB belongs to the n by n matrix. It holds that. No, this is not correct. We solved something like this in the introduction of the multiplication of matrices, because once you try to multiply these brackets, you will have AB plus BA, and they are not equal to each other to put them this like, so it's not correct. A belongs to the n by n matrices and it is invertible matrix, then for any B and P, the matrix B and the AB have the same rank. Yes, it's completely true and it is direct. It's a logic. So in order to do this, the matrix B will be with the dimension of the result matrix. As you can see, the questions are accessible, yet needs concentration and a very good understanding about everything. Let's go to the question number 6. Question number 6, it's about, yes, just a sec, it's about vector spaces. He is asking you, consider in each of the indicated vector space the usual operation of addition and scalar multiplication. So it's really exists. Under these conditions, answer the following, and he is giving you more than one question. For this slide in specific, I will do this question in the next slide with a lot of details, but I wanted you to have a chance to look to this question for my students who I'm going to send them the PDF. So those are the questions. And of course, we will see the correct answers. They will be A, B, and E, and we'll go through them shortly in the coming slide. So let's do question number 6 once more. Now I will need to check the first answer if it is correct or not. He is asking you if A, which consists of A, B, C, and D, R belongs to R4 or is a subset of, I'm sorry, this is the form of this set of vectors in R4, where the condition A and B equal to 0, which means A is equal to negative B, and B plus C plus D is equal to 1. And he is telling you this statement is not a subspace of R4. Now I will try to remember what are the conditions for a subspace. Number one, the existence of the origin, the closure addition, and the addition closure, and the scalar multiplication closure. But before doing all of this, I should get the generators or how to represent this subspace or this set of vectors. So the best idea is to get shape or the function of the set, check the conditions for this sub-vector space. So if it's gonna be A, B, C, and D, I will use the first information, which is A plus B, to replace A by minus B. I will leave B as it is, and I will go for C. From this equation, I will let C equal to 1 minus B minus D, and I will make the replacement. And this is where 1 minus B minus D. The last one, I will leave it. Now, I have just only two variables that appear in the general set. But unfortunately, for component number 3, if you remark, there is one number which is positive 1, which doesn't belong to the B or the D variables. And this is why it's going to destroy the claim that it is a subvector space. So the first thing to do is trying to isolate or to distribute this guy. So I will consider it negative V, B, and the negative V. That's the first vector. And we did that previously. The first component is equal to 0, second component is equal to 0, but the third component is going to be negative D, and the fourth is positive D. So these two guys, and if you add them together, it will give you most of the components, but missing the positive one in the third component. So you will have to add this vector. As I told you, that's the problem, because B and D will belong to R and will be multiplied by this guy, which means I will have B times negative 1, positive 1, negative 1, and 0. I will have D times 0, 0, negative 1, and 1. The B and D can be any value belongs to R, which will lead to that those two guys, those two vectors, if they were just only these two vectors, it's going to be a sub-vector space. But unfortunately, for this case, we have 0, 0, 1, and 0, which prevent the 0 vector from happening in this subvector space. It's not the 0 of R4, which is 0, 0, 0, and 0. And this is why it's not going to be a subvector space from B and D. So let's read it once more. It is not a subspace of R4, so that's a correct statement. Please be careful about what's correct and what's not correct and how it is written. So that's a correct statement. This subvector space doesn't a subvector space from R4. Now I will go for F. F, this is related to a set of n by n matrices. But it's talking specifically about the matrices, the n by n matrices, where the matrix by itself is equal to twice the transpose. And this will never happen unless you are dealing with a zero matrix. Yep, it is a subspace of the n by n matrices. The matrix with this condition must be the null matrix, and it is a subvector space by itself from the vector space of the n by n matrices, so it is correct. For F, A and A square, such that A doesn't belongs to R, is a subspace of R square. No, that's a question needs a good understanding. First of all, if you look quickly, you will find that A belongs to R. So if A is 0, you will have 0 and 0, which is the 0 condition and it belongs to R square. If you have A and A square and you add it on B plus B square, the result will be A plus B and A square plus B square. So it looks like the addition closure already exists. If you multiply by a certain number, the first and second component, it will be the same. So also the scalar multiplication is going to be correct. So I would choose correct answer, but no. Because for addition process to be correct, this property must hold in A square plus B square equal to A plus B square, and that's impossible. Because if you have A square plus B square, you will get A plus B to the power of 2, which is A square plus 2AB plus B square, which means that 2AB should equal to 0, and this is not correct. So, and the 4, so once more, it is not a subspace of R2 simply because the failure in the addition closure and the scalar multiplication closure also. If I have U and V belongs to S, we would need A squared B squared to equal to A plus B to the power of 2. But as I told you, the existence of 2AB will prevent this from happening. And also for the scalar multiplication, alpha times A squared and the scalar K, so K times U, it will be, should look like this. But for K times U equal to C, and you make the substitution, it's gonna be that case. It will be, it's not gonna be, this case supposed to be K square, but instead you had A as an A times A square as a condition, and that's also a contradiction, so this guy is not correct. Of course, from the definition of the vector space and subvector space, this is not correct number D, because the vector space and the subvector space should be not empty set. It contains at least the 0 or the null vector, so it's not correct. Let F be a subspace of vector space E, and let U and V belongs to E. And if U and V belongs to F, and U belongs to F, then V belongs to F. Yes, it's completely sensible. It is logic. Since U with V and U belongs to F, the both of them belongs to E, and even F is a subset from E, so V must exist in F. I brought all of this for you, but unfortunately I had to add the insert the remarks in this way. This is why I've doubled this slide twice for you in order to be able to go through it easily. Okay, let's go to question number 7. Question number 7, it's going to be a direct one. It's not going to be difficult. He's giving you two matrices, and under these conditions, indicate which statements are correct. The matrices A and B are both invertible. This is really very simple to check. All I have to do is to evaluate the determinant of each one of them. I've wrote this in here. Easily can be checked by evaluating the determinant for each one of them. I think the first one will be, this is 0, this is going to be 0, that's going to be -2, and that's a 0, and that's positive 4, so the result of this determinant is equal to positive 2. Okay, keep it with you. But while for B, the multiplication of the principal diagonal is 2, and this is 0, and that's 8, the sum is 10, while on the secondary direction, this is negative, and this is -8, and this is -2, so it's a 10 minus 10, so it's equal to 0, which makes a very good sense also, as I told you. So number E is he's asking me the matrices A and B are both invertible. This is not correct. Just only one of them is invertible and the other is not invertible. A is invertible, but B not invertible. Number B, the reduced echelon form of the matrix A is the identity matrix. Of course, since determinant of A doesn't equal to 0, then we will be able to get the identity matrix from this matrix. So it is correct. For C, the system AX equal to C is a consistent system for any matrix C. So this system AX equals C is a consistent system for any value of C, uh, 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 yes, as long as A matrix doesn't equal to the determinant of A matrix doesn't equal to 0, and so this is going to be a consistent system for any value of C. It's not even depend on C because of the rank of the coefficient matrix, and the augmented matrix will be exactly equal to the number of variables, so you will have a consistent. The reduced row echelon form for matrix B, the matrix is this one. So all I have to do is to try to get the reduced echelon matrix for B. Multiplying the first row by negative and add it on the second row. Multiply the first row by -2 and add it on the last row. Then finally, you will have to multiply by a half. This 2 is going to be 1 and eliminate it. So that's the row reduced echelon form for matrix B. And of course, it doesn't equal to number D. Finally, determinant of A is correct because determinant of A is equal to 2, and we already evaluated. So if you look to this question, that's one of the fastest questions. It takes almost no time. So although there is some questions burning time in the exam, others you will be able to solve them quickly. Question number 8, indicate which statements are true, and I believe also it's going to be really very handable. The product of any two elementary matrices is also an elementary matrix. Yes, of course, because just a second, please. The reduced is asking you the product of any two elementary matrices is also an elementary matrix. This is not correct. The product of any two elementary matrices is going to make a matrix with two operations, more than one operation, so it's not going to be an elementary matrix. So this question is not correct. Okay, he is giving you the reduced echelon form of the matrix A, the identity matrix, of course, and the determinant is not 0. I'm sorry, it seems like a copy from the previous slide. For number B, for any matrix, there exists B 3 in 1 such that 2103 is a solution of the system X is equal to B. Once more, remark that for any matrix which is M3 by 4, that means 3 rows and the 4 columns, 3 rows and 4 columns. For this class of matrices with 3 rows and 4 columns, he is asking you by the matrix B, which is the result, whatever you change it. Is the solution 2103 the solution of the system, or there exists a matrix like number B? Yes, it's correct. The reduced row echelon of the matrix A is the identity matrix, of course, as it determines it doesn't equal to 0. Okay, for question number C, the matrices 1003 and 001 and 2 and the matrix 1039, 1015 are row equivalent. In order to check this, try to get the reduced echelon form for both of them. If it is the same, so they will be equivalent. I remark that the first matrix is in reduced echelon form, so I will have to work out the second. I think multiplying the first row by a negative and adding on the last row will give you this guy. And then dividing the last row on -2 or multiplying by -1/2, you will have this new row. Multiply by -3 and add, and this is the matrix that you are comparing. 0, 0, 1, and 2, and 1, 0, 0, and 3. So it's not the same. So no. The matrices are I'm sorry, it's exactly the same. So the matrices are equivalent as you saw. For question number D, the identity matrix of order 3 is not an elementary matrix. This is not correct because all the elementary matrices are unit matrices, even the unit matrix by itself. And for the last question, he is asking you about, he gave you, this is something like also a question that been in the previous exams. So, if you try to evaluate this guy, I believe it's going to be a very good idea to use the fourth row or the fourth column. I think I used the fourth row, so it's going to be negative j, negative for the algebraic complement, Eliminating row and column, you will have a 3 by 3 determinant also containing I and double zero. So expanding the last column, the result that you should have is negative JIAD. Instead, you have ADGI. I can replace the values, but the sign is missing, so it's not correct. So for any A, B, C, D, E, F, it holds that the value of this determinant should equal to negative JID, and this is why I didn't choose it. Question number 9. You have an A which is a 3 by 3 matrix such that the A times adjoint is equal to 4I3. This indicates that A minus 1 is equal to A minus 1 from here, because A times A minus 1 should suppose to I. So dividing on 4, it means A times 1 over 4 A adjoint is equal to I, which means A minus 1 is equal to a quarter in adjoint matrix of A. That's the value of A minus 1. So the matrix A and the adjoint are not both invertible. No, both of them are invertible. So it is not correct answer. The reduced echelon form of the matrix of algebraic complement A and A dash is the identity matrix of order 3. Yes, it's correct. Because mainly their determinants is not going to equal to 0. So you can get the reduced echelon form, which is a 3 by 3 matrix. The matrix joint A has rank of 3. Yes, correct. And all of this from the beginning, because you have value for the inverse, the existence of the inverse. It's equivalent to that. The rank will be the same. It's equivalent that the determinant is not going to be equal to the determinant of the adjoint matrix 64. I don't think I have enough information, because the only information that I have is just this one. So this is not enough information. From the given in this problem, it's not enough to determine the value of this guy. The matrix A is invertible and the determinant E minus 1 is equal to 1 over 4. Yes, already right. Because the determinant of A is equal to 4 and the determinant of A minus 1 is 1 over 4. So we are all set. As you can see, the question is very quick, just needs your concentration and you will be in a good shape. And that's the final question. And he gave you a matrix with A, B, C, D, blah, 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 and also similar to one of the questions that we saw previously. He is asking you, under these conditions, indicate which statements are true. For this guy, for this determinant, it's equal to 6 beta. Okay, let's look closely. The first row was multiplied by 2, so I will multiply by 2 for the value of the first determinant, so it's a 2 beta. The last row, we already changed the second and the third row. The second and third row. So there is a negative sign. So for the time being, it's a negative 2. Then multiplying one of them by 3, so it's supposed to be negative 6 beta. He's giving you 6 of beta. You are missing the sign, so it's not going to be correct. Is determinant of A equal to determinant of negative A? This is not correct. Because as you saw, A is a 3 rows. So if you multiply by negative the value of the matrix, the value of the determinant will be multiplied by negative 1 to the power of 3, which is supposed to be negative of determinant of negative A. So this guy also is not correct. For the last, for the other, for number C, we multiplied the first row by a half and we multiplied the last row by 2, and we made some operation of addition of rows, so it should be a beta exact. The first row will multiply the value by half, the last row will multiply by 2, so they will diminish each other. Determinant of A cube plus determinant of A square of A transpose is equal to B cube plus beta. Yes, it's completely right, because the determinant of matrices once is equal to the determinant of the first times the second times the third matrix, which holds the property that determinant of A cube is equal to beta cube. The determinant of the transposition doesn't it change the value of the determinant, so it is correct from the general properties and the propositions. The matrix A is invertible. The determinant A minus 1 times AT is equal to 1. Yes, correct. Because A transpose is the A matrix. So A minus 1 times A, it means that the value of the determinant is going to be beta. And this value is going to be 1 over beta. So multiplying them together will equal to 1. Guys, this is question number 10. And as you saw, I didn't feel the time with you going through each question. Of course, preparing these slides it takes time because I'm writing the statements, I'm writing the remarks, I'm trying to put it as much as possible to be handable for you, trying to go through each one of them. I wrote the answers for you for and the clarification for each one of them. So please be calm, solve step by step, and don't feel down. Just study well, do practice enough, and you will be in a very good shape. This is the shape of the exam paper. Usually it will come like this. Those are the questions arranged for you. Try to choose wisely, please. After you solve the questions, this is going to be the paper that I really want to have, or the paper that will be collected from all of you. So please do concentrate while you are moving your answers from the questions to the bubble sheet. Finally, if you have any further questions, please do not hesitate to write on the comments or send me on the WhatsApp. You are always welcome. Once I have a time, I will answer you directly. Pleasure to all of you. Thank you very much and enjoy the rest of your day and the best of luck in your exam. Thank you. I'm really very happy that I could, with the current circumstances, to record this session. Thank you very much. Thank you all. Best of luck for you.